The next bit here, which is down here. Okay, more security engineering, which is going to start cryptography, which people get all upset about because there's a little bit of math in it, but it's not too hard. So in cryptography, cryptology is the science, cryptography is secret writing, and cryptanalysis is finding weakness in cryptographic systems to break in. So cipher is the algorithm, which is the mathematical process of converting plain text to ciphertext. Plain text is unencrypted stuff you can read, and you're trying to turn it into ciphertext, which hopefully nobody can read except a person who has the key and is authorized to read it, and they can decrypt it to get back into plain text. That's what you want. So the main thing you're producing here is confidentiality. Because it's encrypted, people can't read it unless they are the authorized party holding the key. Also, it provides integrity, typically as a side effect, in that if they can't decrypt it, they can't modify it in a way that would change the meaning in a controlled way. So authentication verifies the identity of a user. Non-repudiation means you cannot deny what you did. So it has audit records that are accurate, so you can't deny what you did later. And confusion is a desirable property of a cryptographic system, which means there is no relationship between the plain text and the ciphertext. So as I mentioned before, previous versions of HTTPS had a flaw that you could tell the size of the data packets by the size of the encrypted data packets, and that's a failure of confusion. There's information in the encrypted text that gives you some knowledge about the plain text. And diffusion is another desirable property, that the plain text should be dispersed throughout the ciphertext. So any part of the plain text that changes should change randomly half the bits of the ciphertext. So substitution is one method where you replace one character with another. This provides confusion. And permutation rearranges the letters, and that provides diffusion. So cryptographic strength is measured. A strong encryption is very difficult or impossible to decrypt without the key. And you measure that by a work factor. How long will it take a system to break in? The secrecy of the system does not provide strength. This is a very common flaw. People just conceal what algorithm they're using, and they think that's secure. This is called security through obscurity. It's a really bad idea because, for one thing, the secret will tend to leak out. And for another thing, there are really only a small number of systems people use. People can probably guess. And the ones that are well known and published are the ones that have been found to be very strong. So whatever modification you make is probably just a mistake making it weaker. And you'd be better to just use a standard system like AES and not keep it secret. That's why I say don't roll your own crypto. Never invent your own cryptographic. Just use the standard stuff like RSA and AES that has been time tested and you're trustworthy. If you're making something up, unless you're one of the 10 smartest people on earth with a PhD in mathematics, you are not as smart as you think you are, and you are not making something better than these systems that have been developed over years and analyzed by experts. So monoalphabetic ciphers take one plain text letter and turns it into one ciphertext letter. And if it's always the same, then you can easily break this by frequency analysis, because the most common letter in English is E, and then T, and then A. So you can quickly, even from a few sentences, you'll have enough samples to pretty much narrow down the possibilities. Polyalphabetic ciphers use multiple possible substitutions for each letter to prevent frequency analysis. So they're all based on modular arithmetic, like a clock face, where because you want to feed in bytes going 0 to 255, and you want the encrypted stuff to still be bytes going from 0 to 255. So you really do your math on a ring like this, where you go around a clock, 1 plus 1 is 2, and 8 plus 1 is 9, but 11 plus 1 is 0. Again, so you never get out of this range from 0 to 11. That's the idea. Then exclusive OR is a big part of most encryption schemes. It's not strong enough by itself, but it's part of the scheme. So the plain text and the key are just bits, and if the bits are the same, the answer is 0. And if the bits are different, the answer is 1. That's exclusive OR. And so exclusive OR reverses itself. If you have attack at dawn and you put a key called apple, 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 and encrypt it, it turns into this junk. And if you just encrypt it again with apple, 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 it becomes clear. Because another way to look at XOR is when the key is 0, you don't change the input. And when the key is 1, you flip the bit. So this 1 flips to 0, this 0 flips to 1, but this, so that's the point. And therefore, the key bits of 0 are unchanged, the key bits of 1 flip, And if you encrypt it a second time, the key bits of one flip again, getting you back where you started. So exclusive OR, the decryption algorithm, is exactly equal to the encryption algorithm. All right. So when you're encrypting things, you might typically encrypt data at rest or data in motion. Data at rest is the stored data on the hard drive, so it encrypts it when the power is off. Data in motion is transmitting over a network. And so what you typically would like is end-to-end encryption, where only the recipients at both ends have the key, and all the intermediate providers like your internet service provider and so on do not have the key, and they can't see what you're doing. This is the protection that virtual private networks provide. And then there's protocol governance. You have a lot of considerations. How fast is it? How strong is it? How much does it cost? How complex it is, and so on. There are many different encryption algorithms that are customized this way, just like you customize other security measures to get the right balance of confidentiality, integrity, and availability. All right, so let's try another Kahoot, which would be 3F. And here it is. There you go. If that person wins, I'm going to have trouble writing down their name anyway. Yeah, lots of punctuation marks. All right. All right, so a video shows Marjorie at a meeting so she can't deny it. What have you accomplished here? This actually happened to Marjorie Taylor Greene a few years ago. Probably outdated. People have probably forgotten this. She claimed not to have been at a meeting, but they had a video of her at the meeting. Of course, these days you would just say AI made that video. Anyway, that's non-repudiation, where you can't deny what you did. All right, so Caesar moves each letter 3 steps in the alphabet. What's that? That's substitution. Each letter is replaced by another letter, but it's always the same letter for the same input letter. All right. What systems resist frequency analysis? Those are polyalphabetic systems where the same input letter might be any of several different letters after encryption. What's 17 mod 5? To be fair, I don't think they put this on the CISSP exam. It It's in the chapter, but when I took it, they seemed typical managers afraid of math. Anyway. Yep, a lot of people know it. It's 2. You divide by the mod and take the remainder. So 17 is 15 plus 2, because 0 is 0, 5 is 0, 10 is 0, 15 is 0, because you go around the loop, and the loop only has 5 elements. So this is 2 passed a multiple of 5, or 2. What's 3 XOR 4? Another one, you gotta know your binary. And once again, I'm not sure they'd have binary on the CISSP exam. I kind of doubt it. I don't think I saw it. But they certainly have unfair things. All right, it's 7, and let me just explain that in case people don't know. So what you do is you write them in binary. So 3 is 1, 1. 1, 2, and 1. This is a 1 on the right is number 1s, that's number 2s. And 4 is 1, 0, 0. And so when you do the XOR, you get 1, 1, 1, because the bits are different. So that's 7. That's why it works in that regard. Anyway, there you go. Let's see who the winners are. Right, Pedro. All right, and I think I can do the third section here before we start doing the student presentations. So, the history of cryptography. The Spartans had this system where you would wrap the message around, write on it, and then when you unwrap it, it would be hard to read because it would have the letters in some pattern, like every 5th letter or something would be what you do. This is transposition. It doesn't change the letters, it just rearranges their order. Caesar had, I say, a substitution cipher, where you just move A to D, B to E, C to F, and so on. Microsoft still uses Route 13, which is a version of the Caesar cipher, which is pretty ridiculous. And then there's the Vignier square, a polyalphabetic cipher where you'd have a key, and so you would choose, the key would tell you which alphabet to use, and then you would encrypt each letter with that alphabet, and then use it. The key might be Apple, so the first letter is encrypted with the A row, the next letter with the P row, next one with the P row, next one with the L row, next one with the E row. So different. If you had letter E, it would keep coming out to be different replacement letters. That's how the polyalphabetic cipher works. This is a modern cipher disk to like do this automatically with spinning wheels. And this is a Confederate state cipher disk, which basically does the Caesar cipher for you. It's got letters and another batch of letters, and you can rotate this to quickly do Caesar cipher. Wish I could go back in time, so that I'll always have a calculator with me now, so I'm not scared of math. Yeah, there's no reason to be afraid of math. It's not that hard. It's just people have bad experience in the American educational system. All right, so book cipher is a popular one, and boy, they used it a lot. When I went to DEF CON, they had a great presentation of all the encrypted messages in the London Times in the 1800s. That was the only way to communicate with ships at sea, was to put encrypted messages in the Times, and they would pick it up at ports of call. So anyway, they used the book cipher a lot. So you just have a series of like page, paragraph, and word in a book, and all you have, the other person has to have exactly the same book. So this works. And you have to figure out what a common book was people used at the time. And of course, one problem is maybe the word isn't in the book, especially if you choose an old book like the Bible, and so then you're going to have occasional clear text words just mixed in with it. Then there's running key cipher. Like I said, you have a phrase or document as the key. So you take like the Constitution, we the people, and you use that as the key. This is a variation of the one-time pad, really. And then there's code books. This was very common in the early days. Telegraphs used code books just to make the messages cheaper. You would have a common phrase like, I want to change the price of this item, and you turn that into like a 12. So you use less key. That's a common code. And of course, the Secret Service used code names for the first family. Donald Trump is mogul, and so on. They use code for these things. The one-time pad is the perfect cryptographic system. If you have a pad of random letters, and the sender and receiver both have it, and you encrypt the letters one by one using the random letters. You cross them off as you use them, and you never use them again. So this is mathematically unbreakable. The only way to break it is to get that pad. There is no mathematical pattern in the encryption, and if you try to take something that's been encrypted with the one-time pad and try to decrypt it, if you have a message of 100 letters, you will get all possible combinations of 100 letters. You'll get every possible message 100 letters long, and no way you can tell which one is right. This is the perfect unbreakable system. It's been around for a century. No one has ever found a flaw with it. The only problem with it is key distribution. You have to somehow deliver a large amount of key material to the other person securely, and you have to never reuse it. And that turns out to be such a problem, this is almost never used. You'd have to, if you send a megabyte of key to the other person, you'd be able to send 1 megabyte of data, and then you somehow have to send them more key. So it's a problem that way. But nobody can break in by analyzing the ciphertext. So the KGB used one-time pads, but it was broken because they cheated and reused the pads. If you reuse the same pad for 2 messages, it becomes trivial to break, and it's a project in my classes. My programming students are doing it, my Python class. It's extremely easy to crack then. If you use the same pad twice, it shatters like glass. This is the problem with cryptography. You really have to obey the rules. A small change in how you implement it can ruin it. So Hebron machines were large manual typewriter-looking things, and they would encrypt and decrypt data like the Enigma machine used by the Nazis, and the Japanese used it, and the USA used it. These were basically mechanical calculators to implement a substitution system that was very strong. I think it had like a 48-bit key, which was good enough in like the 1950s. There was no way to break in. And then there's cryptography laws. In effect, until 1994, it was illegal to export cryptographic data, so this is why you could not send Windows XP Pro outside the US. They had a special version, crippled version of Windows XP to send outside to other countries, and this was a huge problem. The cryptographers opposed it, and they were right, because they had this version of Windows called K that used really short encryption keys that were easy to break, and that was the only version you could ship to certain foreign countries. So anybody that wanted to make a website that would serve data to, say, China and Russia had to make it accept that low encryption, so it poisoned the web with servers that will step down the encryption to a low level. All the cryptographers said, don't distribute bad cryptography and start using it. Anyway, the Wassenaar Arrangement came out in '96, and that relaxed a lot of these restrictions, although I was still not able to teach cryptography in China. I tried, and they said you won't be allowed to do it because of US export restrictions, and that was true. So the 3 kinds of cryptography are symmetric, asymmetric, and hashing. Symmetric is the most common type that's been around forever, where you have a key and the other person at the other end has to have the same key in order to decrypt it. Asymmetric, each user has 2 keys, a public and a private key, and you never have to deliver a secret. Hashing is not a way to encrypt something, it just is a way to put a fingerprint on something so you can tell if it's been modified. It provides integrity, not confidentiality. So symmetric encryption, you have a secret key, you have to somehow distribute that key to the recipient, and so the question is, well, if you have a safe way to distribute the key, why don't you just send your message that way? But you do something like distribute the key face-to-face and then they travel, that sort of thing. This is symmetric encryption. Stream ciphers encrypt 1 bit at a time. This have a stream of bits. This is what wired equivalent privacy used. Block ciphers are far more common. You have blocks, either 64 or 128 bits, and you encrypt a block of data at a time. An initialization vector is added to it before encryption, so that if you have 2 identical plain text messages, they don't encrypt to the same ciphertext. And chaining is a system of using the result of one block to create the initialization vector for the next block, so that, again, if you have blocks of identical data, they will not have identical ciphertext. Data encryption standard was the algorithm based on IBM's Lucifer algorithm. IBM made a very strong encryption system with a 128-bit key, but the NSA, without explanation, lowered it to 56 bits and created the data encryption standard, which was recommended by the US government for decades, but is no longer considered secure. But it did define the modes. You have electronic codebook, cipher block chaining, cipher feedbook, output feedback, and counter mode. And electronic codebook is the simplest. They also call this textbook encryption. You just take each block of plain text and encrypt it with the key. That's it. So if you have another block of plain text that looks with the same plain text, you'll get the same ciphertext. Yeah, and I see some questions here. Enigma machine used distributed code books. Yeah, you'd have to send it for permutation. But the one-time pad, you need to have 2 copies of the pad. Yes, you have to have one for you and one for the other end. Yes, there have to be exactly 2 copies of it and no others. And Navajo is the only unbroken encryption. Well, the one-time pad is essentially perfect, but Navajo is another way, yes. If you have some language that only a few people speak, that would do pretty well. So anyway, the problem with electronic codebook is it does this. If you encrypt this image, it turns into that, because all the blocks of yellow turn into green. So you still can see a lot of the data here. That's the problem with electronic codebook mode. Identical regions of plain text turn into identical regions of ciphertext, so there is some information still left in the ciphertext, and that's not what you want. So you use CBC mode, cipher block chaining. That will add a random initialization vector to the first block, and then it'll use the encrypted data from the first block to encrypt the second block and the third, so it'll turn into this, just random snow. That's what you want. This is what you want an encrypted image to look like. All information is gone. You have no idea what that picture is. And that would be true of all these other methods we talked about too. They all do essentially the same thing. They will all scramble this to total snow. The only difference is exactly how they create a different initialization vector for each block. So single DES was the original implementation with a single 56-bit key. 56 bits is not enough. They were able to break it by brute force in the 90s, so it's not secure. So they invented triple DES, and the reason for this was if you had a bank and you already had a bunch of single DES equipment and you want to gradually move to a stronger system, you use triple DES because triple DES used 3 rounds of encryption. You'd encrypt, then decrypt, then encrypt again with 3 different keys. And if you set all 3 keys to the same, it would be equal to single DES. So you could buy equipment that could be more secure, but you could run it in the less secure mode for compatibility with your old equipment for a while you have time to replace it. Anyway, if you use 3 rounds of encryption, you get up to 112 bits of security, which is considered very good. Anything above about 100 is considered essentially unbreakable. All right, IDEA was another symmetric cipher, an international replacement for DES, and it has a 128-bit key and considered reasonably secure, but it is encumbered by patents. AES is the standard that everybody likes. The current US recommended standard, it has keys from 128 to 256 bits. It's an open algorithm. You can use it without paying anybody anything, and it uses the RIN-jail algorithm. This is considered effectively perfect and unbreakable. The only real threat to it is that in decades when quantum computers get 1,000,000 times better than they are now, you might be able to crack AES 128, but even quantum computers will never be able to crack AES 256. So we probably don't need another one of these anytime in our lifetime. A private key system. The current private key system is very good. And so here's the finalists. They had a competition for years where IBM and everybody else would send up their best. They all competed, and the one that won was RIN-jail, the one they chose to make AES. And therefore, the ones that did not win this competition, some people prefer them because some people have a cynical attitude about the US government. And they imagine that if the US government approves it, they probably put a backdoor in it. This is what Pavel Durov, the creator of Telegram, said. He said, I wouldn't use your American encryption. That stuff is all backdoored by the CIA. So what you do is you use the runners-up that were never approved by the government, but are almost as good. And that's what some people would do if you don't trust the government. Of course, if you want to work with the government and sell your stuff to the government, then you use the official government-approved system. So there's a RIN-jail algorithm that shows you how it goes. It basically does, it substitutes things, then it shifts rows, then it mixes columns, adds a round key, and does this a series of rounds. It's simple mathematical operations, easy to perform and easy to reverse on a modern computer. But it turns out to be extremely effective. They've been using it for a long time, and nobody's found any significant flaws in it. Blowfish and Chewfish were invented by Bruce Schneier, a very famous cryptographer, and they have a variable key size, so you can try the effects of key sizes. Again, they're open, unpatented, and freely available, so people can use this if you don't trust the government. You might use these, which are still considered quite good, but they don't have the official stamp of approval of the National Institute of Standards. RC5 and RC6 are other ones that are various key sizes out there. And asymmetric encryption is the next category. So if you want to communicate with someone over the internet, like Google, you don't have any way to send a private key to Google. So you can't use private key encryption. So what you do is you perform the Diffie-Hellman key exchange, which was a military secret for 20 years, used by the NSA, but then reinvented by Whitfield Diffie on the outside, reinvented by mathematicians. And so this had been around since the 70s. And so each user has to make two keys, a private key you never tell anybody, and a public key which you tell the whole world. Now anybody can send you secrets, anybody can encrypt stuff with your public key, and you're the only person that can decrypt it with the private key. So you can receive secrets. You cannot send secrets. That's the problem. Your person to receive your message must make their own public and private key pair. So you can't push a message on people. They have to prepare themselves to receive one. That's the only part that's annoying. So this is like a mail slot in your door, right? You have a door, anybody can put mail in your door. You can put a mail slot in your door. If this is a strong door, anybody can put messages in there. Nobody can take them back, but you can't deliver anything to anybody else. They have to make their own door with their own mail slot. You can receive secrets, but you can't send secrets. That's the only irritating part about it. Which got Ed Snowden in a lot of trouble. Ed Snowden wanted to leak national secrets from the United States to a journalist, but the journalist was non-technical, and journalists could not create a key pair. They couldn't understand what he was saying. He was recording YouTube videos trying to tell them how to make a key pair, because he knew even the NSA can't crack this, so he tried to use public key encryption, but the journalists couldn't figure it out, so they had to bring in a tech expert, so now more people are learning these secrets than he intended. But that's a problem with public key encryption. It's technically complicated to set up. But our browser does it pretty well automatically. Anyway, one-way functions are, this is an essential part of almost all cryptography. There has to be some mathematical process that's easy to do in one direction and hard to reverse. So you can encrypt, but it's hard to decrease. That's what you want. So you need a one-way function. Factoring a large number is the one used by RSA. So if you multiply two prime numbers, that's easy to create another number, but to find the prime numbers and reverse that is very difficult. The discrete logarithm is a similar process, and elliptic curve is effectively the same kind of thing, where you have a process, a one-way function. It's easy to do one way and hard to do the other way. All three of these are going to be destroyed by quantum computers if they ever improve to a very, very good. So symmetric algorithms use shorter keys and are faster. And so in RSA, what you do in HTTPS on the internet is you use asymmetric encryption just to deliver an AES key, and then you use AES. So you don't have to bother using this slow, complicated algorithm longer than necessary. So there are recommendations for key sizes, and the current recommendation through 2030 is that you should have at least 112 bits of encryption of security, and so they recommend these key sizes like we should be using for symmetric key algorithms. We should be using AES 128 or 256 is what's recommended, of course. And for SHA digital signatures, we should be using SHA 256, I think is what they like. SHA 1 is no longer recommended, not considered strong enough. SHA 224 or higher is what's recommended. And for asymmetric encryption, I'm not seeing it here, but that should be, the asymmetric encryption, they did change their mind and say we're going to have to switch to quantum safe algorithms pretty soon. So hash functions. The original one most people used was MD5. Before that, there was MD4, which is what Microsoft used for their passwords, and they're still using, which is a sin and a shame. But anyway, MD5 is insecure. There are ways to forge it and ways to fool it. SHA-1 is no longer trusted either. That's why everyone's expect. The only thing recommended is SHA-2 of at least 224 bits or longer is what's considered to be a unique fingerprint for a file now. And collisions. A hash function should be unique in practice, so you shouldn't be able to find two files with the same hash. Then you know if the hash matches, that file is intact. Now, in principle, there have to be two files with the same hash, but you make it so rare that you can never find them. And that's what happened in Google found, in 2017, Google found the first SHA-1 collision. They were able to make two files that had the same SHA-1 hash. That's the sense in which SHA-1 is no longer trusted. But SHA-2, there are no known collisions, and no one expects anybody to find any anytime soon. But they did already figure out what to use for SHA-3 in case SHA-2 falls. But as far as we know, SHA-2 is all, as far as we're going to have to change anything during our lifetime. So let's do one more Kahoot, and that'll be it for this stuff today. This is 3G, and there it is. All right. All right. That's a system people use. That's what one of the major generals in Washington used to share secrets with his foreign lover. He would write emails and put them in the draft folder, and she would log in and see them. Well, there's various flaws. One thing, you could think it's secure because they both know the password, and they don't tell anybody else the password.
No one knows you're using it for secret messages.
That's true. It's covert in that regard, but the email service provider has access to those messages. So if you send them a court order, they would see it, I think.
Can I just get a virtual contractor that's encrypted, and then somehow I send her a password?
Well, if you control the server,
No. I put a virtual contractor that's encrypted.
yeah, but if you're using a service like Gmail, it's on their server.
No, I'm saying you upload a virtual contract encrypted on your computer. Say 500 megs, for example. Then
Well, if you encrypt something yourself, then it's private key encryption, and nobody will get in if you don't give them the key. That's right. All right. But that trick with the email is essentially just security through obscurity. It's a covert channel. You hope nobody knows you're sending those messages. Yeah. It's not really protected by cryptography. It's protected by secrecy.
it's a low security, basically.
Well, that depends. Secrecy is often all you have. I mean, if nobody figures it out, you're okay, but... All right, let's take a look at these.
Well, I can always give the person my virtual floppy or something, and then they can open the virtual hard drive with the virtual floppy with my
Then you've got private key encryption. You'd have to give them a password.
I'll just give them a virtual floppy.
Yeah, but they'd have to have the password if it's encrypted. Yeah. Then it's essentially private key encryption. All right, let's take a look at these. Good. All right, so... All right, what's the strongest system on this list? One-time pad is the strongest in the world, beats everything. It has a big key distribution problem. But if you're willing to distribute the key, nobody's getting in there, not without the key. All right, what process uses no key? That's hashing. Hashing is not encryption. It can't be reversed. It's just putting a fingerprint on a file. It's done with no key. There is a thing called a keyed hash, but that's not normal hashing. All right, what cipher encrypts the bits one at a time? That's a stream cipher. Encrypt the bits one at a time. One great thing about it is you do not need to pad blocks to fill a block. So anyway. Which mode preserves some patterns in the input? This is a serious deficiency. Electronic code book, also called textbook encryption. It's one of the many flaws I find frequently in Android apps. Android apps are a great showcase of terrible encryption. Anyway. What's the weakest scheme on this list? Microsoft is huge, and they've done a lot of things. What, this one? Well, Android is like the early days of Microsoft, like, Windows 95 or DOS, it's making mistakes that Microsoft hasn't made in decades. DES is the weakest one, the one so bad it's no longer considered secure. All the rest of these are considered pretty secure. DES is the one that has been broken for decades, and nobody should be using it anymore. All right, which one is popular on mobile devices? I don't know if I mentioned it, but we'll mention it now. Elliptic curves are the most popular because they use shorter keys, so they use less CPU and less battery power. So they're better for public key encryption on mobile devices. All right. Well, let me stop this recording.